We're now moving to Patrick Warrington of Calrec, who's going to be talking about network technologies in the specific context of Calrec Hydra 2. Patrick.
Thank you. I think we're entering into quite an interesting time. We've been talking about developments in audio networking today, but it's not just in audio that there are developments happening. It's in video as well, and people are starting to look at what the possibilities might be, and they're starting to talk about the idea of an IP-era broadcast facility and the possibility of a single infrastructure that might be able to carry audio and video and maybe comms and control information and synchronization information, and maybe you can do your offline file transfers on it and perhaps even send the occasional email as well. In fact, it's starting to feel a bit like we may be just on the cusp of a revolution. I mean, a genuine paradigm shift in the way that broadcast systems can connect together. And it might go further than this as well. It may be that we eventually can start to redefine or rethink about the geographical relationship between the venues where live sports and live entertainment happens, and the control surfaces where the creative stuff happens, and the DSPs where it all ends up getting rendered. So, a revolution. And I would argue that we're probably overdue a revolution in the broadcast industry, because we've been using the same technologies for transporting audio for, well, forever. You know, analog. I know in the 80s we got some digital and that was quite good, but it was this century, this millennium, before we really started to have some audio networking technologies that were worthy of the name. And you know the ones: Ethersound, CobraNet, WheatNet, Livewire, Calrec's Hydra 1. So it's not surprising that people are getting pretty hyped and excited about some of the new AOIP and video IP technologies. But I don't think that it's necessarily going to be a smooth road to the new IP era. There may be a few bumps and a few potholes on the way, and I think we might do well to be very cautious and conservative about how we adopt these technologies, and perhaps look at an incremental approach to adopting these technologies. If we're going to have a revolution, then let's try and keep the body count as low as possible. Now, what might a pragmatic approach to adopting IP technology look like? Well, I think the first thing that we need to do is to understand that there are sweet spots for audio networking technologies, just like there are for conventional interconnection technologies. There are application sweet spots where technologies are quite well suited, and other applications where they're not quite so well suited. And I've got a model that I like to use to try and find a way to think about this. There it is. There seem to be some food metaphors cropping up this morning. I call this the onion model, the broadcast audio onion model, because it's got layers, not because it will make you weep, hopefully. And it's just a model. The real world doesn't break down as cleanly as this, but I think it does help to provide some insight. So I'd just like to spend a moment or two talking through this. At the centre of this model, well, what it's attempting to do is it's attempting to define some distinct application areas within the broadcast audio environment. Now, at the centre of that, I've got this area that I've called signal acquisition. But this is all about, well, acquiring the signals. It's about the microphones on studio floors or on people's lapels or on the field of play, and their connections to the audio mixing console, where an audio operator is going to make program feeds, and they're going to also make, well, lots of feeds, but they're going to make monitor feeds that are going to have to find their way back into the ears of commentators and presenters. So latency is very critical in this part of the application space. Now, in the old days, of course, this was all analog. It was microphones plugged in directly to mixing consoles or perhaps through patch bays and tie lines, early networking. But more recently, mixing console manufacturers have offered stage boxes, the boxes that you can put on studio floors that have got the microphone preamp circuitry in there and the ADC circuitry in there, so you can capture the sound much closer to the source, convert it to digital and get it back to a mixing console maybe several hundred meters away without any further loss of quality, and perhaps have some control information going back from the console back to the stage box so that you can control the mic amps. So that's the centre part of this model. Then the next ring, I've called it the infrastructure, and this is about the connections between the various different bits of broadcast kit. Okay, so it's connections from the broadcast console to comm system, to video routers, to DAWs if you're recording the event, and maybe you've got some other mixing consoles on there if you've got backups or you're doing some submixing. And the important thing about connections in this part of the application space is that, well, they are highly multi-channel. You're usually transporting a lot of signals. They're a lot more tolerant to latency, generally speaking. They tend to be a lot more fixed. Well, there isn't really a need for dynamic routing of signals in this part of the model. They're just big pipes, audio pipes, connecting bits of equipment. So technologies that are popular here, MADI is the real big hitter here, but there's SDI and people use AES3 as well. Okay, so that's that layer of the onion. Now the outer ring is about wide area networking. It's off-campus connections and contribution and distribution. But I'm not going to talk about that because, well, the rest of this presentation doesn't really deal with that. So I'm just going to ignore that part of the model. So hopefully, if you're prepared to accept this premise, then we can start to see how some audio networking technologies map differently onto different parts of this model. And the part that I'd like to start off with is the center. So the bit that I've called signal acquisition. Now, so far, we've heard people talk about AVB and AES67 and Ravenna. And what I'd like to do is to talk about a different audio network that hasn't been mentioned so far today, and that's Calrec's Hydra 2. And the reason why I want to talk about that is because it's a network which is specifically developed to operate in that part of this model, that central part of this model, which puts it slightly at contrast with some of the other AOIP technologies. So, Hydra 2. Well, the best way, I've only got a short amount of time, so the best way I think for me to talk about Hydra 2 is to explain how it came about. Now, back in the early 2000s, some of Calrec's customers came to us and said, can you come up with some technology, some products that will allow us to use our facilities a bit more efficiently? What they wanted to do was to put stage boxes into their studios and have those connect up to consoles in different control rooms. They wanted to be able to use any studio with any control room. And they wanted any console to be able to control the mic amps in any of the stage boxes. Now, there's various different reasons why people wanted to do this. Sometimes it was about just more efficient use of studios. Sometimes it was about being able to very rapidly switch production teams by switching control rooms, just perhaps during the commercial break. Sometimes it was just about having some elegant contingency in case some disaster befell one of the control rooms. But whatever the reason, we thought this looks like a fantastic application for an audio network. So Calrec went and designed Hydra 1, which is an Ethernet-based networking technology. And it was really just a network that was designed to allow the sharing of access to stage boxes. And it looks like this. Now, when we designed this, we came up with one guiding principle to it, and that was that we wanted to make sure that the workflow for the audio operator wasn't complicated by the fact that an audio network was being used. So audio operators could use locally connected I/O, and they want to use also some network connected I/O, and we didn't want to present them with some complex new control screens that would make the job more difficult and more complicated. So we did that, and we ended up creating something that was quite powerful, because what it meant was that audio operators could patch local signals, they could patch network signals, and they could store them in memories, and then later on they could recall them, and at the touch of a button, hundreds of network patches could be made. So quite sophisticated and quite novel at the time. And people like that, and it was quite a successful product. But we learned a couple of things pretty quickly. First of all, we learned that a system based on Ethernet, designed in the early 2000s, doesn't scale as well as you might expect. Now, we got quite big. We could have up to 8 consoles and 32 stage boxes on that network. But if we added more than that, then it started to not be reliable, which of course wasn't acceptable. The second thing that we learned was that, yes, while it's very powerful that you could, at a touch of a button, deploy lots of network connections, you could get yourself into quite a lot of trouble as well. There was definitely potential for resource conflicts and disasters, taking people off air. That could have happened. So what Calrec ended up doing was to start to develop some quite sophisticated ideas around port ownership and port protection, and the resolution of resource conflicts. And this had to be more sophisticated than the sort of basic port locking, cross-point locking that you'd get in a conventional audio router. So we did this, and this worked quite well. But as we installed systems around the world, we started to realise that this wasn't ambitious enough and that we needed to do something bigger. And so we started to develop Hydra 2. And Hydra 2 took the whole concept of an audio network to a new level. Because instead of just having a system that was about sharing access to I/O, everything ended up being part of the network. We abandoned the idea or the concept of directly connected I/O completely. Everything was networked, including the inputs and the outputs of a console. So, there we go. So it looks a bit like this. The idea was that we would create a network which was based on distributed TDM routing. Okay. Now we wanted to scale the whole thing up so that you could have any number of consoles on there at any time, and maybe tens of thousands of I/O ports as well, because that's what the larger broadcast facilities were requiring at that time. And this is what it looks like physically, but in fact I've come up with this diagram, which is, I think, more helpful when you're trying to figure out how to think about Hydra 2. So you can see the blue boxes on here they're cross-point routers, 8,000 by 8,000 TDM-style routers. So you have 8,000 inputs, 8,000 outputs, a very low latency switch, one-to-many routing. And they're connected by very high-capacity links. Those are the heavy blue lines on that diagram. So you can see how you can build a network of TDM routers. And you'll see that some of those routers have got DSP in them. So you can take a router core and you could plug a DSP card into that. And it then becomes a router core and a console core. And you can connect up a control surface to that, and you've got a mixing console. And any of those blue boxes can have up to 32 stage boxes or I/O boxes connected up to them. So you can see how you can start to build a network. Now, in order to make this work and to have the latency kept really low and to have absolutely deterministic routing so that you were never trying to make a route and suddenly found that for some constraint of the infrastructure you weren't allowed to make that route, we couldn't allow that to happen. In order to achieve those design goals, we had to make a decision to abandon the use of off-the-shelf IT infrastructure. So we abandoned the idea of using switches from HP and Cisco. And that was quite a critical decision to make. It was also a very liberating decision to make, because once you do that, it frees you up to design the network to work in any way that you like. You can design it exactly to the purpose that you want without having to deal with the compromises of a packet forwarding paradigm. But it also meant that we had to develop our own network control software to replace that. Now that was a good deal of work, but because it was bespoke, it meant that we could build in some functions and some capabilities that were specifically designed to support broadcast workflows. Now there were a lot of them, and I can't talk about all of them, but there are one or two that I think, or a handful that I think are worth mentioning, so I will very briefly. So I mentioned before about port protection. This is a crucial function. In Hydra 2, we retained the same port protection mechanisms, but we were able to add into that functions that, once conflicts had been identified, provided a very sophisticated way in which you could resolve those conflicts without any danger of taking anybody off air. We were asked to introduce a concept of access rights as well by some clients, and this is a mechanism by which you could hide some I/O resources from some consoles. This was so that some of our clients could protect some of their very high value live streams. They didn't want people in neighbouring studios being able to get hold of them accidentally or on purpose. So it provides an extra level of protection and security. We have a system of port aliases, which is quite arcane, but what it's designed to do is to allow you to very rapidly switch the control room which is servicing any given studio at any one time. And you can do that very rapidly at the touch of a button without any kind of repatching or having to work with an audio router or a network control screen. And it happens in a few seconds. We developed the idea of Hydra patch bays, and this is a way of creating a virtual patch bay inside the network fabric. Now, it allows you to do quite a lot of things, does this, but the principal thing or the main thing that it allows you to do is for an audio operator to publish some of the outputs from the mixing console into the network so that they can be picked up by anybody else. They can be seen and picked up by anybody else on the network, and the operator doesn't have to worry about patching to a lot of different destinations. So it helps with flexibility. We also decided that we would like to expose the cross points, some or all of the cross points on the network, to control by third-party routing systems like VSM and everts. And this really helps to support the idea that this Hydra 2 network can replace conventional audio routing. And we've developed a standalone application that allows you to do some port patching and create salvos and deploy salvos as well without having to be sat at a console. So this network, in summary, it's like having audio routing performance but built into a network. You can have 20,000 I/O ports, and you can patch them to any of 20,000 input ports and patch them to any of 20,000 output ports. Or you could have one input port and patch it to 20,000 output ports. That kind of flexibility is just not practical using off-the-shelf IT switches. At the moment, you need bespoke hardware to do that. And that's what Hydra 2 provides. So hopefully, I've been able to show that the Hydra 2 network is designed specifically for that application space at the centre of that onion model. So let's take a look at the next layer, the model, the infrastructure layer. Now, this is where the incumbent technologies are MADI and SDI. Well, this looks like the perfect application space for AOIP and AVB technologies. And the reason for that is that they've got the capacity, they've got the interoperability. That's really important because this application layer is about connecting third-party pieces of equipment. Well, you can imagine, we've seen a picture of it earlier on, actually. I think Mark provided a picture. It was ABC, where you saw a man practically entombed in a tunnel of wires. Well, with AOIP solutions, we should see that dwindle down to just a handful of wires carrying perhaps the same number of signals, or maybe even more signals. It's going to be an extremely elegant solution indeed, because AOIP is scalable, it's very cost effective, and it's reasonably flexible. I say reasonably flexible. I mean, it's compared with having to repatch physical cabling. It's flexible because it's probably going to be much simpler and easier to redirect an audio stream than to go and start to mess about with cables. Now, it's worth pointing out, these benefits don't come for free. There's probably quite a lot of design effort needed to design an IT network that is going to match the traffic profile without any risk of oversubscribing any parts of the network. And there's going to be some work to set up QoS and PTP and maybe other protocols that you need. And you may need to set up a SIP server or something like that. But once you've done that, and those streams are up and running, then there doesn't seem to be any reason why they wouldn't continue to work absolutely flawlessly. But I want to point out, I think this is an important point, that using AOIP technologies in this way is really a cable replacement kind of application, a very sophisticated cable replacement application. And it's different to the Hydra 2 type application in the centre of this model, which is about dynamic, push-button, salvo-type audio routing, on-demand audio routing that has to reconfigure very quickly. They're two different and contrasting application areas. It's a bit of a generalisation. I know there are probably people who might argue a little bit about that, but right now, I think that is the case. And it may change in the future, but that's the case as the world is right now. Now, I did talk about AOIP and AVB technologies in the same breath, but they're not all the same, clearly. And I would like to offer you my AOIP cheat sheet, which is a very quick look at the top 4 AOIP technologies. I include AVB in that as well, the top technologies. And this is from the point of view of a console manufacturer. In other words, the point of view of an organisation which is neutral about the technology but is going to have to deal with the nuts and bolts of implementing these technologies. So I'm going to start with AVB. I know we've covered a bit of this, but it probably doesn't hurt to go over it again. AVB, the trump card for AVB is that it has this reliable streaming performance that Jan talked about early on. But it also has another trump card, and that is that it's got a ratified discovery and stream management protocol as well, ratified by the IEEE. It doesn't get any better than that. But it needs this AV-capable switch fabric, and as far as I know, at the moment, there are 2 switch manufacturers who make AV-compatible switches. That's Arista and Extreme. So we're still waiting for Cisco and HP to jump on board. But you could argue that you've got two, do you really need any more? The other thing about AVB is that it is limited to a single subnet. It truly is a local area networking technology, which is great for the sort of applications that I've been talking about. Now, there is some talk of giving layer 3 capability to AVB. It hasn't happened yet, but it would be a great thing if that does actually happen in the future. The next one is Dante. Now, there isn't anybody here from Dante, from Ordinate, so it falls to me to speak on their behalf. The first thing to say about Dante is that it's a proprietary technology, so it has to be licensed. So when a manufacturer makes a Dante interface, they have to pay a license fee, which at some point will be passed on to customers. But for that license fee, you do get quite a well-developed, sophisticated product. It does work, it's out there, there's lots of installations. In fact, there's an impressive and growing list of licensees. Last time I spoke to Lee Ellenson of Ordinate, he told me that there were over 100 companies that were licensees now, but when I went on their website a couple of evenings ago, I could only count 84. Maybe there's a few in the pipeline. But it also has this Dante controller software application, which is quite a sophisticated, centralized way in which you can do your connection management. So it's probably about the most advanced of the current crop of AOIP technologies. AES 67. Been talked about already. It's worth pointing out it isn't a protocol, it's an interoperation standard. So if it were a protocol, it would have some bits missing, some quite significant bits missing. It doesn't have the discovery or stream management mechanism built into it yet, but I think that there's work being done to address that. But the really important thing about AES 67 is because it's been ratified by the AES, it has a huge amount of momentum behind it. It sort of feels like it's going to happen, come what may. People talk about it being the lingua franca of IP audio. And lastly, I don't think Andreas would forgive me if I didn't mention Ravenna, and Ravenna, of course, deserves to get a mention. It's a very flexible AOIP protocol, and it is a complete protocol definition. It does have discovery built into it. I'm sure Andreas will correct me if I'm wrong, but I don't think it has a stream management protocol built into it, but quite a few people I think are using Ember Plus for stream management, so it's becoming an informal part of that protocol, and Andreas is nodding, so I think I'm right about that. But that's a very useful informal addition to the protocol, and a great big tick for Ravenna because it interoperates with AES 67 as well. There's two thoughts. I'll be very quick, a couple of minutes.
Please.
Two thoughts that I'd just like to leave you with. The first one of those is that it's quite clear that we have a nice array of AOIP protocols to choose from. And maybe they'll all thrive and survive, or maybe a few will wither away. But the transports aren't going to be the problem. But what I think is, if not a problem, it's certainly not quite so clear, is how management of these systems will work. It's certainly not clear how a large multi-vendor network of AES 67 might work at the moment in a way that is centrally managed and would be acceptable to a large broadcast facility. And I'm not saying that there won't be solutions to this. I'm absolutely confident that there will be solutions to this management problem, but it's not clear where they're going to come from. It could be that they come from within the broadcast industry. It could be that the traditional broadcast infrastructure manufacturers provide them, or maybe the people who are going to make the great big video IP routers of the future, or maybe console manufacturers, or maybe it'll come out of somewhere outside the industry. Maybe if the answer to this management problem is going to be SDN, software-defined networking, it could have come from Cisco or HP or some company that we haven't heard of. I'm sure that it will come. But early on in my talk, I sort of suggested a cautious approach, and maybe an incremental approach would be a good way to adopt this technology. And in the spirit of that, I'd like to just offer a last idea. I call this the hybrid network. Okay. And this is a way in which perhaps we can quite quickly come up with a practical network that leverages the very sophisticated network management software that we have already in Hydra 2 and the AOIP infrastructure benefits, so the benefits of AOIP devices. So I think this diagram is fairly self-explanatory, but on the right-hand side we have a Hydra 2 network, on the left-hand side an AOIP network. Now, sure, you can connect to AOIP devices using the sorts of streams that people have been talking about, and that will work just fine. But if you have an AOIP device that has ports on it that you think really need to benefit from the kind of push-button salvo-type routing and perhaps some of the other sophisticated network management functions that I talked about earlier with Hydra 2, then perhaps what we can do is connect those devices wholesale, all their inputs and all their outputs to an AOIP Hydra 2 interface and have them attached to the TDM router that Hydra 2 provides, so that they can benefit from the TDM cross-point matrix kind of routing that Hydra 2 offers. This may be attractive for some people, but the exciting thing about this is that virtually all the piece parts for this exist already, or if they don't, they're going to be available very soon. So a network that works a bit like this hybrid network, could be a reality very soon. Okay, that's me. That's
Brilliant.
me finished. Thank you.
Thank you, Patrick.